Hola, hi, this is Al, your statistics instructor. Let's begin. So let me show you what's the plan for this video. Okay, so the main idea is discussing the duality of moving average and autoregressive processes. I would like to talk about these three things. The backward shift operator. We're going to introduce that operator in this video. It's going to help us write in a more compact fashion the equations that define our time series processes. Number two, we're going to talk about a few examples, how we can use this backward shift operator to rewrite some processes that we have encountered in the past already. And number three, we're going to combine all this to rewrite an autoregressive process of first order as a moving average. Okay? Okay, so here we go. First, let's define the backward shift operator. Okay? Definition of a backward shift operator. So we're going to be using capital B to denote the backward shift operator. And we're going to apply that to a time series xt. Okay? And what that backward shift operator is going to do is that when applied to a time series xt, what we're going to end up with is with the lagged time series. Okay? So we're going to end up with x at t minus 1. Make sense? Now, instead of using this notation in the future, b applied to xt, we're going to be doing it just like this, b xt. Okay? Now, examples. Let's talk about a few examples. It turns out that you could apply the backward shift operator multiple times. Okay? So, for instance, we could write b squared xt. So what we mean by that, let me do it step by step, is we're applying the backward shift operator twice. So first, we apply it to the original time series xt. We know that the result of bxt, of applying the backward shift operator once, it's going to be just your time series at t minus 1. Okay? And then you apply the backward shift operator to xt minus 1. So what you end up with is x at t minus 2. Make sense? Okay. So now let's talk about another example. This would be our first example. Let's call it that. Let's talk about another example. Remember the autoregressive process of second order? Let's write that one down, okay? Let's see, x at t will be the same as a sub 1 xt minus 1 plus a sub 2 x sub t minus 2 plus wt. Where wt, this guy here, represents a Gaussian noise, is a Gaussian white noise, right? So what we know is that Wt has a normal distribution with mean 0 and variance sigma squared, okay? Okay, so now let's apply the backward shift operator to rewrite the AR2 process, okay? Here we go. So let me copy paste this. Now what I would like to do is to rewrite the right hand side of this equation using the backward shift operator. So let me do this. We know that this is going to be the same as a sub 1, and this one here, x at t minus 1, is the same as b applied to xt. You guys agree? So let me take this one here and borrow it. On the other hand, right, we have a sub 2 times x at t minus 2, right? So what we know is that we could rewrite this term as b squared times xt, or b applied twice to xt. Make sense? Then we have the Gaussian noise. Okay? Now furthermore, let's do something here, okay? We can see that xt here is a common factor, okay? So let's try and factor it out. So let me copy paste this. And now what we're going to be doing is rewriting this just like so. Make sense? So xt is a common factor, so we just factor it out, and then instead of having a sub 1 be xt plus a sub 2 b squared xt, we have this term inside those square brackets. Now let me write the xt down on the left hand side. And now how about we place all the x's on one side, on the left hand side, and then we leave the Gaussian white noise on the right hand side. Okay. So now let me rewrite our last equation like this. Okay, so you can see that we could factor out that xt. So that's what we're going to be doing next. So what we have is 1 minus a1b minus a sub 2 b squared. Okay. So what we have done here is we have rewritten this, an AR2 process, using the backward shift operator. Okay, makes sense? If you have a chance, okay, later tonight, rewrite an MA process as an MA2, a moving average of second order, as you know, using the backward shift operator. Okay. So it's going to take a minute. Okay. I just want you to you know, feel comfortable using this backward shift operator. Now, we said, remember at the beginning of this video, that we would like to eventually rewrite an autoregressive process of first order as a moving average. Okay? So before we get to do that, what I would like to do with you here is talk about another example. Okay, this is going to be slightly more complicated than the one we discussed here, rewriting the autoregressive process of second order using the backward shift operator. Okay, so what we saw is that we went from this expression for the autoregressive process of second order to this expression in terms of the backward shift operator. Okay. So the next example is going to be slightly more complicated, but it's going to allow us to rewrite an autoregressive process of first order as a moving average. And that's, if you will, that's the ultimate goal of this video. Okay. So let's talk about a more complicated example of using the backward shift operator. So what I would like you to do is, what we're going to be doing together is we will rewrite the following process using the backward shift operator. Let me write it down, the original process, then we're going to see how we can do this with the backward shift operator. Okay, so we have xt plus 1/2 xt minus 1 and then we have 1/4 xt minus 2 and then we have 1/8 xt minus 2, that's what we should have here, xt minus 3 plus dot dot dot. Okay, so that's the process that we would like to rewrite. As you can imagine, the next one is going to be this one. The first one is 1/2 to the power of 0, right? That's the first coefficient that you have here, that one. Then you have 1/2, then you have 1/2 squared, then you have 1/2 cube, and so on. Okay, so we want to rewrite this process using the backward shift operator. Okay, so solution. So we note that this one here, x at t minus 1, could be re-expressed like this. The backward shift operator applied to xt. This one here, x at t minus 2, would be the same as b squared applied to xt. This one, b cubed applied to xt. Okay, so let's do that. So this one equivalent to, let's write what we said. So we have here b applied to xt. Here it would be b applied, but b squared to xt. This one would be b cubed applied to xt, and so on. We need a cube. Right. Okay. So now let's do what we did before, right? We realize that xt is a common factor. So let's rewrite our last expression. So what we have next is this. We could have a 1. Let me do this. Let me borrow this guy. Let me place it outside. So I'm going to have a 1, and I'm going to have b, and I'm going to have b squared, and I'm going to have b cubed, and so on, right? Let me place all this inside some brackets. Okay, can you see that? By the way, remember that when we do this, b applied to xt, we end up with xt minus 1, but instead of writing that, this operator, in the future we're going to write this down like this. We're not going to be using this notation. We know that it's b, that b is an operator, so b is applied to xt, but you will be writing this down like that. Okay? So we have factored out that xt. So what we can see is we have this expression here, 1 plus 1/2 b plus 1/4 b squared plus 1/8 b cubed, and so on. Okay. Now let's take this to the next level. We know that b represents an operator. Okay, we are aware of that. But let's now use what you guys know about geometric series to rewrite this expression inside these square brackets. Okay. So let me open a new one here so we can recall how we can, so we rederive the formula that you may need to find the value of a geometric series. Okay. So you know that the trick goes like that to derive that formula. First you do a finite version of the geometric series. So let us start at 1 plus r squared plus r cube plus dot r to the power n. Okay. So what you do is now you multiply both sides by r. Then what you have is r squared, r cube, r to the 4th, and so on, right? And then r to the power n plus 1. So now we take these two and we find the difference between them. So Sn minus Rsn equals 1 minus r to the power n plus 1. Okay, so now let's factor out Sn on the left hand side. I have 1 minus r. On the right hand side you have 1 minus r to the power n plus 1. Finally, let's divide on both sides. Okay. So now, if you take the limit as n goes to infinity, okay, and r is in absolute value less than 1, lim n goes to infinity. Let's see, where do we have that? That's here. So the limit as n goes to infinity of this will be just 1 divided by 1 minus r. But that is provided, right? Provided the absolute value of r is less than 1. Okay? So bottom line, so we had the geometric series, and then the value of that geometric series is just is going to be 1 over 1 minus r. provided that the absolute value of r is less than 1. Okay, so can you see that we have something very similar here? This is not the one we want. The one we want is here. Let me find it. This is the one. So can you see that we could rewrite this using that formula we just derived? Okay, so let's write it down like that. So this here inside these square brackets would be the same as 1 divided by 1 minus v divided by 2 in this case. Times xt. Great. Now let's talk about this condition. Remember, this one here, b is just an operator. It is not a number. So the condition is that for that geometric series to converge is in terms of this coefficient, okay, or these coefficients, okay. So let me just argue why. Again, the condition will be given in terms of these coefficients only. Can you see that if you ignore b, it is clear that r in this case will be 1/2, okay? So let me justify why you end up with this, okay? So let me rewrite this guy inside those square brackets using that shorthand notation that you have seen in the past for series. Okay, let me use, this is the same as k, well, the summation k goes from 0 up to infinity of, let me write this one down like this, b divided by 2 to the power, oops, sorry, not what I wanted to do. Let me redo this one here. Here what I want is just k. Okay, I'm just rewriting what we had inside those square brackets with that shorthand notation. Okay. Now, what I want you to see when you see that notation is this. Okay. This, just this, what's inside those square brackets, is the same as this. Let me write this one. Let me rewrite it like this. B to the power of k times 1/2 to the power of k. Agreed? Now let me expand this. This would be 1 plus b applied to 1/2, right? That would be the first term, plus b squared applied to 1/2 squared, which would be 1/4, plus b cubed applied to 1/8, and so on. Now let's think for a sec what this means. This is a, if you think about it as an xt, this is a constant. So if you apply the backward shift operator to a constant, so that constant at the previous time is going to be still just a constant. Same goes for the rest. Now, let me rewrite this. So again, when you apply the backward shift operator to a time series that is constant, then you end up with that same constant. If you apply the backward shift operator twice, same result. 3 times, same result. So the convergence here, so meaning what allows you to go from this kind of expression to this, is the fact that here r is in absolute value less than 1. Okay, makes sense? Okay, so now that we have talked about this kind of a slightly more complicated example of an application of the backward shift operator to re-express a time series, okay? Now, let's do the last example, the main example of our video. What we wanted to do is to rewrite the autoregressive process of first order as a moving average using this new notation that we have introduced, this new operator, okay? So let me do this in a new page. So let's do that one. We will show that the process, and let me write that one down, the AR1 process can be expressed as a moving average, okay? Let me use A as the only coefficient that we have for that autoregressive process of first order. WT, just like before, represents Gaussian white noise, okay? Where WT is Gaussian white noise, meaning the WTs are IID, independent and identically distributed. They are normally distributed with mean 0 and variance sigma squared. Okay, so what we want to do is rewrite this guy here as a moving average. Can be rewritten re-expressed, let's say, expressed as a moving average. Okay, there we are. Okay, so solution. So let's consider a moving average that it's kind of crazy the first time that you see it like that. But remember, you guys have experience with this. So let me define a new time series, a new process that goes like this. X sub t, it's Wt plus a Wt minus 1, or W at t minus 1, plus now I will have a squared at minus 2 plus, you can imagine what the next term will be, a cube x at, well, w at t minus 3, and so on. Now, let's apply the backward shift operator to the right-hand side of this equation. And let me, since I am using xt for the original AR1 process we are interested in, let me refer to this guy as xt star, okay? Okay, so these two are different, okay? Okay, so as I was saying, let's apply the backward shift operator to the right-hand side of that equation we just wrote. So what we're going to have is, instead of Wt, what we're going to have is just A1 times Wt. Makes sense? Another way of thinking about this 1 would be as b to the 0 power. Make sense? Okay, now instead of Wt, we're going to have the backward shift operator applied once to Wt. Instead of having Wt minus 2, we're going to have the backward shift operator applied twice to the white noise series. Same goes for the next term, right? Instead of W at t minus 3, we're going to have b cube applied to the white noise series, okay? So that's what we have here. Make sense? Yeah, and this would be just Wt, right? Now, just like before, we could factor out the Wt, okay? Let me do that next. So we have this as a common factor, okay? Make sense? Okay, now take a look at this expression inside those square brackets. We could rewrite that using the formula for a geometric series, okay? So let's do that. Let's rewrite what's inside those square brackets with the formula that we previously found. So this 1 plus ab plus a squared b squared plus a cubed b cubed plus so on, right? We know is equivalent to this using that formula, the geometric series. 1 over 1 minus ab. And that is provided that a is in absolute value less than 1. So this is provided that the absolute value of a is less than 1. Okay? Okay. Now, so we have this expression here. Okay? Let me make it look a bit nicer. So we know that our original time series xt star, which is an infinite sum of terms, of white noise terms, okay, is the same as just this 1 over 1 minus ab times wt, the white noise series. Make sense? So first, let me point this out. This is one of the advantages of using the backward shift notation. Can you see that we could express this in a more compact way? So now, what I'm going to be doing next is something quite interesting, I think. So what I'm going to try and do here is apply the inverse operator on both sides. With what we're going to be doing next is we're going to be showing that these operators have inverses. Okay, so I'm going to apply the 1 minus ab operator on both sides of this expression here. Okay, let's give it a shot. Let's say that just to applying the operator 1 minus ab, 1 minus ab on both sides. Let me just copy paste this and do that. Let me pre-multiply by that guy. 1 minus ab. I'm going to be doing that same thing here. 1 minus ab. Got it? Now, what I'm going to be doing on the right-hand side is I am going to be, well, let me copy-paste this one. I am going to be expanding what we mean by this again, so you can see something very, very clearly. Okay, so we have this, no problem, but we know that 1 divided by 1 minus ab is equivalent to this. Okay, so let me copy paste this part here. And then we're going to play around with these terms here. So note that when I do 1, okay, so that is just this guy here, right? 1 times what's inside those square brackets. I'm going to be rewriting that, okay? So that's the first one. then I have negative A times B applied to this. So let me write that one down, okay? That's going to be the interesting part. Let me write it down underneath because that's going to be interesting. So I'm going to have AB times 1. So that's just going to be AB. You guys agree? Then negative AB times AB is going to be A squared, right? B squared. Then negative AB times A squared B squared, negative A cube B cube. You can see that, right? And so on. Let me copy these. So negative A cube B cube, right? That's a product. That's a result of this product, negative AB times A squared B squared, negative A fourth B to the fourth, so on, right? And you can see that all these guys are multiplied by WT, okay? So let me have that here. So can you see that when you do that, 1 plus AB WT plus A squared B squared WT, A cube B cube WT, and so on, these terms will cancel out. The only one that is going to survive is WT. Agreed? So what we have is that this is the same as just this. Makes sense? Can you see it? So what is really surprising is that yes, these we started with the backward shift notation as something that could help us rewrite time series stochastic processes, right, in a more compact fashion. But now it has these amazing properties that these operators have inverses. Okay? Can you see that we went from this and then we just, what we did is, let me multiply by its reciprocal, if you will, and then we end up with only WT on the right hand side. So this will be important in the future when we talk about autoregressive moving average processes. This notation is going to allow us to write those models in a more compact fashion, and it will also have other implications. In a future video, we're going to talk about the concept of invertibility, and again, we will be using this notation, the backward shift operator. Okay, so before we finish the video, right, let's just summarize what we did together. So we started talking about the duality of moving averages and AR processes. We introduced the backward shift operator. we talked about a few examples of applications of that backward shift operator. We talked about the AR2 process, the autoregressive process of second order. We talked about the more complicated process, one with infinitely many terms, and we used the backward shift operator. We saw that using the formula for a geometric series, we could rewrite that infinite sum of terms with, the combination of the backward shift operator and the geometric series formula in a more compact way. And finally, using the backward shift operator and some of the ideas we discussed before, we showed that an autoregressive process of first order is a moving average process. It's a moving average process, an MA infinity, if you will. That's what you showed here, because we started with a moving average, like this one, an MA infinity, and then we showed that you have this. It's the same as an AR1. Let me just underline that here, right? Using this notation, what you end up with is xt star. Let's open the brackets. This one, AB xt star, is going to be just xt minus 1 star and then if you solve for xt star, that's going to be wt, well, plus at minus 1, well, axt minus 1 star plus wt. Okay. Let me write that one there. Let me just write this one clearly. Xt minus 1 star. Okay, makes sense. So we started with an MA infinity, a moving average with infinitely many terms, and we ended up with an AR1. And this shouldn't be a surprise for you because we did it in the past during class in a different way. Okay, but okay, so that's it for now, guys. Take care.